Welcome back to UAP Rant. This is episode 24 now in the series. So one more episode to go to wrap it up. Last few episodes, those that have been following the podcast, we've been talking about the science of UAP and what sort of tools and approaches we need to do in terms of data collection and analysis interpretation when we think in four dimensions or look at four-dimensional concepts, because we're considering time as the fourth dimension being scalar, relating it to Maxwell's quaternion notation, the vector calculus modifications, and Einstein's spacetime. So we're looking at how we apply the science to scalar time and three-dimensional space-time and the interaction between the two in terms of describing UAP, UFOs, and the phenomena. So some of the tools we'll go over. There's just a list here I want to work through, and then we'll wrap it all up in the next podcast. So we need to look at simulation. So we need software that can visualize four dimensions by extending three-dimensional graphics into four dimensions to allow manipulation of objects with an added time dimension in some sort of rotating hypercube. I think they're called tesseracts. There's the tesseract concept, which you see in Interstellar when they're inside the black hole as well. So we need to be able to visualize four-dimensional space, and we need, on top of that, space-time simulations. So we need to have models that incorporate general relativity to simulate the time dilation for wormholes, and hyperspace dynamics when you get length contraction. So that we'd apply that through education and research, through the researchers using simulations to visualize time as a dimension that can be manipulated alongside space. We need machine learning algorithms that focus on the physics or the physical principles to analyze these complex space-time phenomena. Things like neural networks for space-time analysis. So you've got algorithms designed there to identify space-time distortions and predict object behavior in four dimensions. We need to look at data-driven wormhole studies using real-world data. For example, gravitational wave detectors to look at shortcuts through space-time in the scalar fourth dimension of time. So we need also experimental platforms, so quantum experiments, looking at more quantum entanglement experiments to explore non-locality and higher dimensional connections between a scalar fourth dimension and space-time and the vectors in space-time. More particle accelerator research to study particles at relativistic speeds and looking at the interplay of space and time. More gravitational wave observatories. We also need tools to enhance and explain four-dimensional thinking. So some sort of cognitive or thought experiment tools that we could use to develop our four-dimensional thinking for how we perceive space and time. So some VR environments to work within with four-dimensional geometries. We look at gamification, so interactive games to encourage solving problems in higher dimensions. So we could train astronauts or scientists to conceptualize space-time distortions they might encounter in deep space travel, especially if you're applying or using a technology in a craft that's going to jump scalar space and disappear and reappear in space-time through a four-dimensional scalar space. We need to look at philosophical and artistic approaches as well, and how we can exhibit and visualize four-dimensional objects or concepts, and that's where I mentioned the tesseract before that you see in the movie when they're in the black hole for Interstellar. Philosophical studies as well, so historical and modern theories of time and space, and another thing is practical educational curricula around this as well. So we want four-dimensional problem-solving frameworks introduced to curriculum or student curriculum so they can focus on applying four-dimensional thinking to real-world problems linked to logistics and time management and design when thinking in four dimensions. and integrate that into STEM. So STEM isn't robots and coding, that's just a tool, right? STEM, we should be teaching relativity, special relativity, scale of space, four-dimensional thinking, space-time and high-dimensional geometry as foundational topics in physics and mathematics. And I think this is where that whole branch of science is missing in field repulsion theory. So we need to consider that as well. A couple more options here from my notes. So applied analytics and interdimensional understanding, so space-time mapping, so gravitational wave analytics and temporal mapping, so we can correlate events across time to identify causality or anomalies. Energy signature analysis is another one, so you've got spectral analysis, frequency mapping, so identifying energy profiles of objects that are transitioning between dimensions, understanding gravitational and electromagnetic fluctuations linked to higher dimensional travel. And we talked about that with Orban Rod research in the field where we've been collecting data within what we think is an interdimensional anomaly. So looking at how energy cascades, energy coupling and energy harvesting works within these frameworks. And then predictive models, of course, so temporal anomaly forecasting. Where are these temporal anomalies going to occur? Can we harness them and make use of them? So using machine learning and historical data, especially about Earth's geometry, and then hyperspace travel simulations. All right, so there's quite a range there. So the last episode, I want to just wrap this all together and wrap it up, bringing together just an overview and where we might move forward from here. And I also want to talk about Plato's allegory of the cave and how this relates to all of this. So look forward to talking again soon.